Hi everyone, I'm Hangzhe Xie from SenseTime Research. Today I'm going to present our work, Depth-Aware Spacetime Memory Network for Video Object Segmentation. This is a joint work with Yunmu Huang, Anyi Xu, Jingpeng Lan, and Dr. Wenxiu Sun. Video object segmentation is the task of automatically generating accurate and consistent pixel masks for objects in a video sequence. In this paper, we focus on the semi-supervised video object segmentation, which aims to segment particular object instance across the entire video sequence given the first frame ground truth annotations. It is a very challenging task due to the occlusions, drifts, and appearance change of the target objects over time. Many methods for video object segmentation have been proposed in the past few years. Early methods estimate optical flow to check the object masks across frames. However, estimating optical flow can be only used in simple cases without occlusions. If an object is completely occluded and then appears again, the optical flow cannot be accurately estimated. More recent methods use multiple networks for optical flow estimation, object tracking, and RAID. Such a complex architecture elevates the occlusion problem, but it is not time efficient. Moreover, both optical flow and object tracking are not robust to occlusions. Even the latest tracking algorithm cannot get the correct results in this case. To solve this problem, OAL presents the spacetime memory networks to decrease the dependency of temporal continuity. Given the path frames with object masks, the memory encoder generates a key-value pair, where key is used for encoding appearance variance and values stores detailed information for producing the mask estimation. For the frame at time step t, the query encoder auto-generates a key-value pair. The key-value pairs of the time step t and past time steps are fed into the space-time memory reader. The key-value pairs are concatenated in the space-time memory reader. The features generated by the space-time memory reader are forwarded to the decoder to produce final masks. To better distinguish objects with similar appearance, we incorporate depth maps into the space-time memory networks. In both memory and query stage, both frames and the corresponding depth maps are fed into the network. To estimate depth maps from RGB images, we use the work that learns depth of moving people by watching frozen people. The network is firstly trained on static scenes with moving cameras. During inference, the depth can be estimated from moving scenes and moving cameras. Besides depth maps, we also use a modern backbone network, ResNet. The ResNet block incorporates feature map split attention within the individual network blocks. Besides, ResNet requires no more computation than existing ResNet variants. According to the preprint in arXiv, DeepLab v3 with ResNet increases MIOU by 7% in semantic segmentation. In video object segmentation, STM with ResNet achieves better results. Atrous spatial pyramid pooling is composed of multiple dilated convolution layers with different dilations. It is widely used in segmentation and helps to segment small objects. We use Atrous spatial pyramid pooling in the purpose CSTM. Most methods use cross-entropy as the loss function. However, segmentation uses intersection over union during evaluation. To directly optimize intersection over union, we incorporate the Lovász Loss during training. Here are some qualitative comparison results. With the estimated depth maps, the purpose DSTM are more robust in extinguishing background pixels. Here's a video for boxing. And here's another video for diving. You can see that our method performs better than STM. Of course, there are still some limitations of a method. Depth estimation can sometimes be challenging and the results may be wrong. The incorrect depth may lead to wrong segmentation results. In some complex cases, depth maps cannot eliminate the ambiguity. How to segment objects in such cases is still an open problem. Thanks for listening.